Okay, hi guys. Okay, today our group will explain about the phenomena that you guys have just seen before this. So about the phenomena before this, you guys have seen about the structure of salt and rock. Okay, so today our group is gonna investigate about the crystal structure of salt and the crystal structure of another element is rock. Okay, but before that, we have to go to the crystal structure world. So for the time being, let's go to that world. Okay.
Right. So now we are in this microscopic crystal structure world of salt and HCl. So why does salt can be crushed easily? It's been playing in my mind. Why does this phenomenon happen? So after a lot of my research, exactly researchers, I'm gonna tell you guys why does this happen. You guys wanna know? Follow me.
So, I will explain to you guys about sodium chloride NaCl structure. The sodium chloride lattice is phase center qubit, with the basis consists of one Na plus ion and one Cl minus ion spread by one half the body diagonal of a unit cube. In solid sodium chloride, each ion is surrounded by 6 ions of the opposite charge, as expected on electrostatic grounds. The surrounding ions are located at the vertices of regular octahedron. In the language of close packing, the larger chloride ions are arranged in a cubic array, whereas the smaller sodium ions fill all the cubic gaps between them. This same basic structure is found in many other compounds and is commonly known as the halide or rock-salt crystal structure. It can be represented as a face-centered qubit lattice with a 2-atom basis or as 2 interpenetrating face-centered qubit lattices. The first atom is located at each lattice point, and the second atom is located halfway between lattice points along the FCC unit cell edge. The attraction between the Na plus and Cl minus ions in the solid is so strong that only highly polar solvents like water dissolve NaCl well. So, what kind of bonding is NaCl have? or what kind of bonding that table salt are categorized in. So, salt or NaCl is categorized in ionic bond and being called as ionic crystal. These ionic crystals are hot, have high melting points, and are brittle. When they melt, the resulting liquids conduct electricity well. These properties reflect the strong attractive forces between ions of opposite charge, as well as the repulsions that occur when ions of like charge are placed near each other. They are brittle and tend to shatter in smaller crystals when stressed. When a crystal is hammered of stress, ion with like charges are forced into close proximity. The crystal then literally self-destructs because of electrostatic repulsion. So, in conclusion, NaCl or salt are easily to be crushed compared to a rock because it has ionic bonding and is categorized in ionic crystal group, which are easily or tend to shatter into smaller crystals when stressed. And one more point I want to add is because of NaCl consists of non-pure substances, so the force between them are somehow weaker than the pure substance, such as, for example, here, rock or silica. Thank you.
So, you guys already know that salt NaCl is in face-centered qubit, simple qubit, in face-centered simple qubit, and you guys already know that because of salt is in ionic crystal category, they bond by ionic bonding, so that's why salt are easily crushed. And because of salt is non-pure substances, consists of impurities, that's why that is one of the reason why salt so easy to be crushed and to be shattered. So, are you guys satisfied with my explanation? Thank you.
If you smell what the rock is cooking.
Okay, you already see about why salt are easily to break. Now we are in a microscopic world of a silicon. So, why silicon is not easy to break? If you want to know why, please follow me. The rock is made of silicon elements that arrange to form a diamond structure. The space lattice of diamond is face-centered qubit. The primitive basis of the diamond structure has two identical atoms at coordinates 0, 0, 0 and 1/4, 1/4, 1/4 associated with each point of the FCC lattice. Because the conventional unit cube of the FCC lattice contains 4 lattice points, it follows that the conventional unit cube of the diamond structure contains 8 atoms. There is no way to choose a primitive cell such that the basis of the diamond contains only one atom. Diamond structure have the tetrahedral bonding characteristic. Therefore, the diamond structure is an example of directional covalent bonding found in column 4 of the periodic table of elements. Covalent crystal. Covalent bond is a strong bond. The bond between two silicon atoms in diamond with respect to separated natural atoms is comparable with the bond strength in ionic crystal. The covalent bond is usually formed from two electrons, one from each atom participating in the bond. The electron forming the bond tend to be partly localized in the region between two atoms joined by the bond. The spin of the two electrons in the region is antiparallel. The covalent bond has strong directional properties. Thus, silicon have the diamond structure with atoms joined to four nearest neighbors at tetrahedral angles. The strongest binding occur when the spin of the two electrons are anti-parallel. Okay, you already have a basic knowledge about a diamond structure and a covalent bond. Because of the silicon is in a group 4 of a periodic table, it forms a 4 covalent bond between the atoms. Because of covalent bond form, the structure is a diamond structure. So diamond structure is a strong structure compared to other structure. Therefore, silicon is not easily to crush than salt. Thank you.
Okay guys, now we have returned to the real world, to the real realistic world. So, you guys have already know, right? My friend here, my doctor here have already explained to you guys what's the difference of crystal structure between salt and rock. So, you guys have understand the difference of different material have different crystal structure that make it have different physical properties. So, if you have any questions, please email us at our website and you can get the answer you have wanted. So that's all for today. We're gonna vanish, okay? Bye. See you soon.
Video at our website.
Bye.
Get low when the whistle go. Get low when the whistle go.